You look at the sun. You feel its warmth, a benevolent and ancient pressure on your skin. You see its light, the engine of your world, the giver of days, the anchor of your sky. It is the most familiar object in your existence, a constant and unquestioned truth. You think you know it. You think of it as a sphere of pure light, a perfect furnace burning steadily in the void, a symbol of clarity, of reliability, of life itself. But what if this is only the surface story? What if the sun, our sun, the very heart of our solar system, keeps a secret? What if, at its core, beneath the crushing weight of 1,000,000,000,000 tons of hydrogen, there is not a heart of fire, but a heart of absolute darkness? What if there is a ghost in the machine, a specter from the dawn of time, nestled in the center of the light, a primordial black hole? This is not a story of monsters. This is not a tale of cosmic collisions or rogue wanderers threatening our world from afar. The chances of a black hole simply entering our solar system and being captured are infinitesimally small, a statistical impossibility. No, this is a much more intimate, more unsettling possibility. A story about a seed of darkness that may have been planted before the sun was even born. A story that begins not with a threat, but with a question. A whisper in the mathematics of the universe. The story we tell ourselves about the sun is one of purity. It is a story of fusion. In the unimaginable pressure and heat of its core, atoms of hydrogen are crushed together, their identities erased and forged into something new, helium. And in this act of creation, a little bit of mass is lost, converted into a torrent of pure energy. Light, heat, the river of life that flows 93 million miles to our small, blue world. Gravity crushes inward. Fusion pushes outward. For billions of years, these two colossal forces have been locked in a perfect, delicate ballet. This balance is the life of the sun. This balance is the life of every star. It is the fundamental truth of the cosmos, we believed. It is a simple and beautiful story. And for a long time, we thought it was the whole story. But the universe rarely tells simple stories. The universe speaks in whispers, in paradoxes, in numbers that do not quite add up. And in the middle of the 20th century, humanity built instruments sensitive enough to hear one of those whispers. We try to listen to the sun's heart. We try to count the ghosts it produced. We look for its neutrinos. Neutrinos are the phantoms born from the sun's nuclear heart. They are particles so ethereal, so uninterested in our world of matter, that they can pass through an entire planet of lead without noticing it is there. They're the direct, unassailable evidence of the fusion happening at the core. Every time hydrogen becomes helium, neutrinos should stream outwards, a ghostly wind carrying the truth of the sun's inner workings. So we built our traps. We filled vast subterranean tanks with cleaning fluid, waiting in the darkness for the 1 in a trillion collision, the telltale signature of a neutrino from the sun. We listened. We waited. And the numbers were wrong. They were profoundly, stubbornly, frighteningly wrong. We were detecting only a third of the neutrinos we expected. It was as if the sun's fire was banked, burning at a fraction of its predicted strength. But that was impossible. The sun's brightness, its energy output, its gravitational pull on the planets, everything we could see and measure, told us the furnace was roaring at full power. Yet the ghosts, the neutrinos, told a different story. They whispered that the sun was hiding something, that our models, our beautiful, simple stories, were broken. This was the solar neutrino problem, and for decades, it haunted physics. It was a crack in the foundations of our understanding of stars. Science was faced with a phantom deficit, a mathematical ghost it could not exorcise. What was missing? What secret process was at work in the heart of our star? The year was 1971. The world of physics was grappling with this solar mystery, and at the same time, it was exploring the very edge of reality, the consequences of Einstein's equations in their most extreme forms. It was the age of black holes. And in this era of intellectual ferment, a young physicist at Cambridge, his body already failing him, but his mind roving across the entire expanse of space and time, asked a different kind of question. His name was Stephen Hawking. Hawking was not just a calculator of equations. He was a poet of the cosmos. He looked not only at the present state of the universe, but at its very first moments. He imagined the Big Bang not as a smooth, uniform explosion, but as a violent, chaotic, lumpy inferno. In that primordial chaos, he theorized, the density of some regions could have become so immense that they collapsed directly into black holes without ever having been a star. These would not be the giants we hunt in the dark between galaxies, the collapsed remnants of massive stars. These would be different. These would be primordial black holes, fossils of the first second of creation. Some could be vast, but others could be microscopic. A black hole with the mass of a mountain, compressed into a volume smaller than an atom. A black hole with the mass of an asteroid, a city, a planet. Tiny, dense, and ancient beyond imagining. These primordial black holes, he proposed, would be scattered throughout the universe like seeds. Relics of the beginning, floating silently through the eons. And if they are scattered everywhere, then it is not impossible that the cloud of gas and dust that would one day become our solar system contained one. That as our sun coalesced, it drew in not just hydrogen and helium, but also one of these tiny, ancient seeds of darkness. And that seed would have sunk through the churning plasma, through the nascent fires of fusion. It would have fallen inexorably to the very center. There, it would have found a home. This was Hawking's audacious proposal. He suggested that perhaps the solar neutrino problem was not a problem with our understanding of neutrinos, but a problem with our understanding of the sun. He suggested that maybe, just maybe, the sun had a second engine. How could this be? How could an agent of pure annihilation, a point of infinite gravity, be a co-author of a star's life? This was the central paradox. A black hole is a taker, not a giver. It consumes. It destroys. But the physics of a black hole is subtle. It does not just swallow. When matter falls into a black hole, it does not simply vanish. It is torn apart, accelerated to incredible speeds, heated to unimaginable temperatures in a final, desperate scream before crossing the event horizon. This process, called accretion, releases a tremendous amount of energy. In fact, it is the most efficient energy generation process known to physics, far more efficient than nuclear fusion. A primordial black hole at the center of the sun would not be a ravenous monster. It would be a quiet drain at the bottom of a vast reservoir. It would not gulp, it would sip. It would feed on the sun's core, particle by particle, a slow, methodical hunger. And as it fed, it would radiate energy, a quiet, steady hum of power generated not by fusion, but by gravity itself. If the sun had such a second engine, it wouldn't need to burn its nuclear fuel quite so furiously to maintain its outward pressure against gravity. The black hole's accretion energy would be doing some of the work. The sun would still be bright. The planets would still follow their familiar paths. But the fusion rate at its heart would be slightly suppressed. And if the fusion rate were suppressed, it would produce fewer neutrinos. The numbers almost worked. A black hole with the mass of a large asteroid, sitting at the sun's center, could theoretically account for the missing neutrinos. The ghost in the machine had a name. The whisper in the mathematics had a physical form. The idea was stunning. It was elegant. It was also, for a time, pushed to the side. Science, in its wisdom, eventually found a different solution to the solar neutrino problem. We discovered that neutrinos are not as simple as we thought. They are cosmic chameleons. They can change their flavor, their identity, as they travel from the sun to the earth. Our detectors were simply blind to the other flavors. The sun was producing the right number of neutrinos all along. We were just not counting them all. So, the primordial black hole in the sun was no longer needed as an explanation. The case was closed. The beautiful, simple story of a pure, fusion-powered sun was restored. Or was it? The question, once asked, refused to go away. The ghost, once named, continued to haunt the edges of astrophysics. Because even if our sun doesn't need a black hole to explain its neutrinos, that doesn't mean it doesn't have one. How would we know? How could we possibly detect a mountain's worth of mass hidden inside a star that weighs 333,000 times as much as the entire Earth? How do you find a single drop of black ink in an ocean of blinding light? You do not look. You listen. You listen to the sun's song. The sun is not a silent, solid ball. It is a resonant cavity of roiling plasma. It rings like a cosmic bell, vibrating with millions of different sound waves. These waves, trapped within the sun, cause its surface to gently rise and fall in intricate patterns, moving up and down by hundreds of meters every few minutes. We cannot hear this sound across the vacuum of space, but we can see it. By watching the subtle shifts in light from the sun's surface, we can map these vibrations. This is the science of helioseismology. It is our planetary stethoscope, allowing us to probe the sun's hidden interior. Just as the sound of a drum tells you about its size, its shape, and the tension of its skin, the vibrational modes of the sun tell us about its internal structure. They tell us about its temperature, its density, its composition, layer by layer, all the way down to the core. And this is where the ghost might give itself away. A sun with a primordial black hole at its core would be a different kind of bell. The presence of a tiny, ultra-dense point mass would subtly alter the conditions at the very center. The energy generated by the black hole's slow feeding would change the temperature and density gradients in the core. This change, however small, would alter the way sound waves travel through the sun's heart. It would shift the frequencies of the sun's ringing. The cosmic bell would sound a slightly different note. This is the new search, not for missing neutrinos, but for anomalous vibrations, for subtle dissonance in the solar symphony. We're listening for the signature of a process that is not fusion. We are listening for the whisper of gravity's engine. But what would happen to a star that harbored such a parasite? What would its life be like? What would its fate be? This brings us to a new, strange class of object, a theoretical entity known as a Hawking star. A Hawking star is a hybrid. It is a star that is slowly being eaten from the inside out. It is an object caught between two identities, between fusion and accretion, between light and annihilation. In its youth, a star with a small primordial black hole at its center would look almost identical to a normal star. The black hole is too small, its hunger too slight, to make a noticeable difference. Fusion is king. But the black hole is patient, and it grows. Every particle it consumes adds to its mass. As its mass increases, its gravitational pull increases. As its pull increases, its rate of feeding increases. It is a slow, inexorable feedback loop playing out over millions and billions of years. Eventually, a tipping point is reached. The energy generated by the black hole's accretion begins to rival, and then to surpass, the energy generated by nuclear fusion in the star's core. This changes everything. It breaks the fundamental contract of stellar life. The star's core, where fusion is supposed to happen, becomes cooler and less dense than it should be, because the black hole is providing the outward pressure. The star essentially becomes a vast, bloated envelope of gas surrounding a central, non-nuclear engine. Such a star would look strange. It might become what is known as a red straggler, a star that appears younger and more massive than its neighbors in a star cluster, because the internal black hole has stirred it up, bringing fresh hydrogen fuel to its outer layers. As the black hole grows more dominant, the star would continue to swell, becoming cooler and redder. It would be a sun in name only. It would not be powered by a nuclear heart, but by a gravitational parasite, a star whose life is extended, perversely, by the agent of its own eventual consumption. And what is the end of such a star? A normal, sun-like star, when it runs out of hydrogen fuel in its core, swells into a red giant, and then gently puffs away its outer layers to leave behind a cooling, dense cinder called a white dwarf. A Hawking star would have a much more dramatic death. As the black hole consumes the last of the star's material, its growth would become exponential. In a final, catastrophic feast, it would swallow the remaining stellar envelope. The star would simply vanish. It would leave behind nothing but a black hole, now with the mass of a sun, and a faint whisper of radiation. A star gone not with a bang, but with a final, silent gulp. So we search. We listen to our sun, sifting through the seismic data for any sign of this strange, central dissonance. So far, the sun appears to be a normal, well-behaved star. Its song is one of pure fusion. The simplest story, it seems, is the true one. But the universe is vast. There are 100 billion stars in our galaxy alone. 100 billion galaxies in the observable universe. The question is not just, does our sun have a black hole at its heart? The question is, do any stars? The search for Hawking stars has become intertwined with one of the greatest mysteries in all of science, the search for dark matter. We know that the universe is filled with a mysterious, invisible substance that does not emit light, does not interact with us, but whose gravity shapes the galaxies and holds them together. We call it dark matter, but this is just a name for our ignorance. We do not know what it is. One of the leading candidates for dark matter has always been a vast population of primordial black holes. What if the universe is not filled with exotic, undiscovered particles, but is simply littered with these ancient gravitational seeds left over from the Big Bang? If this is true, then some stars must have captured one. Finding a single Hawking star anywhere in the cosmos would be a monumental discovery. It would not only confirm a 50-year-old theory of Stephen Hawking's, but could also solve the riddle of dark matter overnight. It would mean that the missing mass of the universe is not missing at all. It is simply hiding in the form of countless tiny, ancient black holes, and sometimes hiding in the hearts of stars. This transforms the search. It is no longer a mere curiosity about our own Sunday. It is a hunt for the very substance of the cosmos. We scan star clusters, looking for those strange red stragglers. We use astroseismology on distant stars, listening for their songs, hoping to hear that one dissonant note. We're looking for the evidence of a star being consumed from within. We are looking for a star that is also a tomb. And this brings us back to the core of the idea, back to the philosophical vertigo it induces. Think about what it means. If a star can be powered by a black hole, what does the word star even mean? Its identity, its very definition, is predicated on the idea of nuclear fusion. A Hawking star is a contradiction in terms. It is an object that wears the mask of a star, but its soul is something else entirely. Its soul is gravity. Its soul is the void. It forces us to ask, what is the true nature of the objects we see in the sky? Are we seeing them for what they are? Or are we only seeing their surfaces, their masks? How many objects in the night sky are not what they appear to be? This question echoes down into our own reality, into our own perception. You are built from the ashes of dead stars. The iron in your blood, the calcium in your bones, was forged in a stellar core. You have an intimate, physical connection to the lives and deaths of stars. If the sun, the very symbol of constancy and life, can hide such a profound paradox at its center, even in theory, what does that say about the world you perceive? About the solidity of the ground beneath your feet? About the stability you take for granted? Our senses tell us a simple story. A story of solid objects, of linear time, of cause and effect. But physics has shown us, again and again, that this is just the surface story. Beneath the world of our senses lies a seething, probabilistic, quantum reality that defies all common sense. A world where particles can be in multiple places at once. A world where the future can seemingly influence the past. A world where reality itself seems to be conjured into existence by the act of observation. The idea of a primordial black hole in the sun is a perfect metaphor for this deeper truth. It suggests a hidden reality, a central engine, an unseen principle that drives the surface world we perceive, but which operates by a completely different set of rules. the placid, bright surface of the sun, powered by a secret, dark core. Is this not the nature of all things? Is your own consciousness not a surface phenomenon? A bright, coherent story you tell yourself, riding atop a vast, dark ocean of subconscious processes, of biological machinery, of quantum mechanics that you can never directly perceive? You are a walking, talking Hawking star. Your sense of self is the glowing stellar envelope, but your engine, the true cause of your being, is hidden deep inside, operating by rules you do not and cannot understand. What is real in this scenario? Is the real star the glowing ball of gas, or the tiny point of infinite density at its heart? Is the real you the conscious narrator in your head, or the silent, unknowable machinery that gives rise to that narrator? The question dissolves. The distinction itself is the illusion. The star is the entire system, the gas and the black hole, bound together in a single, complex fate. You are the entire system, the consciousness and the biology, bound together in the mystery of existence. And so, we return to the central question. Is there a primordial black hole at the heart of our sun? The current scientific consensus, based on the beautiful music of helioseismology, is almost certainly no. Our sun appears to be exactly what it seems, a magnificent, uncomplicated sphere of fire, a pure star. But the value of a question is not always in its answer. The value of Hawking's 1971 proposal was not that it was right about our sun. Its value was that it was a question that forced us to look at the sun in a new way. It forced us to develop the tools, like helioseismology, to probe its heart with greater and greater precision. It forced us to confront the limits of our knowledge and to admit that even the most familiar object in our sky could hold surprises. And it opened a door to a new possibility for the universe. The possibility of Hawking stars. The possibility that primordial black holes constitute the dark matter we have been searching for so long. The search for these strange, hybrid stars is now one of the most exciting frontiers in astrophysics. We're learning to read the light from distant star clusters, not just for what is there, but for what is hiding. We are sifting through the songs of thousands of stars, listening for the one that rings false. We're looking for a ghost. The final metaphor, then, is not one of a monster, but of a text. The universe is a great, ancient book, written in a language of light and gravity. For centuries, we have been reading the surface text, the bright, obvious words. But now we are learning that there may be a subtext, a hidden story written in a fainter ink between the lines. The primordial black hole is a possible character in this hidden story, a footnote from the dawn of time, whose influence could ripple through the entire narrative, changing the meaning of everything we thought we knew. Astroseismology is our tool for reading this deep grammar of the cosmos. It is our way of looking for the secrets that stars keep. So the next time you look at the sun, the next time you feel its ancient warmth on your face, remember the question. Remember the possibility of the hidden core. Do not see it as a simple, known thing. See it as a mystery, a beautiful, complex, resonant system whose deepest truths we are only just beginning to learn how to read. See it as a reminder that reality is always deeper and stranger than it appears. That even in the heart of the greatest light, there can be a seed of the profoundest mystery. A question that was born in the first second of creation, and which may still be waiting in the heart of some distant, undiscovered star to be answered. The search continues. The listening intensifies. The universe, in its vast and patient silence, holds its secrets close. But it leaves clues. It leaves whispers in the light and echoes in the vibrations of its stars, waiting for a mind curious enough to piece them together. Waiting for you.